All right, greetings everyone. Welcome to the fourth and final video for section 5.2, finishing up our initial study of angles, and we're going to look at some applications of the angle stuff we've been studying. All right, we're going to go back to arc length and then something called a sector area of a circle. And it turns out that calculating both of these things, when you use radian measures for angle measures, are fairly straightforward. So I'm going to give us some formulas here that use radian measures. So for the arc length formula, if we're given a circle of radius r and we're looking for the length of an arc subtended by an angle theta, well, using radians, the formula there is just S equals r theta. And it's really nice, again, see how that's a pretty concise formula, no pi's involved. But what is important here is that that angle measure must be in radians. Okay, this does not work if your angle measure is in degrees. It will not work. Similarly, for sector area, which we can use the symbol A to represent sector area. Well, the formula for that is going to be 1/2 times theta, and again, theta has to be in radians, times the length of the radius squared. So again, see, that's a fairly concise formula. All right, so let's put these to work for us here. So in the first one, we're told that in a circle of radius 5 kilometers, they want us to find the length of the arc that subtends a central angle of 4 radians. So notice we've got a couple of important pieces of information there. Whoops, sorry about that. We're told that the radius is 5 kilometers and the angle measure is 4 radians. Now notice that's not 4 pi radians, it's just 4 radians. So we can just simply use our arc length formula. So S equals the length of the radius. Actually, just do r theta. So then we'll plug in the length of the radius, which is 5, times the angle measure, which is just 4 radians. Again, no pi's here. We'll end up with 20 as our answer. And because we're given some units here, we better use them. So notice that the length of the radius was 5 kilometers. Since arc length measures length, we'll call the units here just kilometers, and that's supposed to be kilometers, not whatever the thing is that I drew. Okay, so 20 kilometers. All right, now our area formula, which is given by 1/2 theta r squared. So here we're told, or asked to find the area of a sector in a circle described above, meaning that we want the same radius, so our radius will still be 5 kilometers. But this time it's subtended by an angle of 72 degrees. Now, again, as I warned you before, in order to use these formulas, the angle measures need to be given in radians. But here we're given one in degrees. So how will we deal with that? Yeah, we'll just convert it to radians. So we'll do 72 degrees over 1, multiplied by pi over 180 degrees. Okay, the degrees can cancel. So we'll end up with 72 pi over 180. Can reduce those. Let's see, that would become, I think, if we put 9 in there, 8 pi over 20, going into both of those, divide by 2 of 4 pi over 10. Oh my gosh, Cody, you could have done this a lot faster. It's like 2 pi over 5. Yep, I think so. So now I've got the angle measure in radians. We know the radius is still 5 kilometers, so we can plug in that information. So we'll do 1/2 times 2 pi over 5 times 5 squared. And we could work that out. I believe if you cancel some stuff there, it'll come out as 5 pi. But if you want to very carefully put it in your calculator. You should get an answer of 15.707. We again want to use units here because we're using area here and the units in our radius were kilometers. This should be kilometers squared. Okay, so the area of that sector is 15.707 kilometers squared, or we could say 5 pi kilometers squared. All right. Another set of examples or applications of this are linear and angular velocity. So angular velocity, you can read the definition here, but it's basically a measure of the amount of rotation that something goes through per a particular unit of time. And in particular, we're going to have the angular rotation. So it might be something like, 3 degrees every minute if we're working in degrees, or it could be 4 pi radians every hour, something along those lines. So it's again, kind of a circular measure of rotation. Linear velocity then is the actual distance that you travel, which in a circle is looking at that actual arc length. So if you think about a wheel rolling along the ground, we could look at like how much it's spinning every unit of time. That'd be angular velocity. But then the actual distance that it covers, that it rolls along the outside of that wheel, that would be linear velocity. Now you see a couple of formulas here, and those can be useful, and you might be able to use those on your homework or on, say, a physics problem. But I find that they're actually not super useful for solving problems like this. So we're going to use a different approach. So here we're told that a car wheel has radius 11 inches, and the car is traveling 30 miles per hour. And we're asked to find that angular speed, and they want us to find it in radians per minute, which means we're going to have to work with some radians. And as I mentioned, it's angular speed, so we're looking at a rotation around the circle, right? So you think about if that circle I just drew is my tire, we're looking at, per every unit of time, how many radians are we rotating through around the circle, going around the outside. And so in order to solve this problem, one thing that we're going to find that'll be helpful for us, since we're going around the outside of the circle, is to find that distance around the outside of the circle, which if you recall, that's called our circumference. Remember, the formula for that is 2 pi r. So we plug in the radius for our circle, our tire is 11 inches. So we'd have 2 pi times 11, which would just give us 22 pi. I'll leave that like that for right now because it'll be useful for us later on. And then also we'll put some units on this. So this is inches since the units on our radius were inches. All right, so let's go about solving this now. And to do this, we're actually going to use some more dimensional analysis here. So since I'm trying to find an answer that's a rate, so radians per minute, and I'm given a rate, 30 miles per hour, I'm actually going to start by writing that rate out, so 30 miles per 1 hour. And we got to somehow convert these units because we want to go from miles per hour to radians per minute. Now, one thing you hopefully see that we could do right away is convert from hours to minutes. So we could do, say, 1 hour is the same as 60 minutes. And the hours can cancel out. And we're just left with minutes as our time, so we're good to go with that. Well, the next thing would be to convert the miles there somehow into radians. And we see over here in our circumference of our circle we calculated, we have inches, so it might be helpful to convert those miles into inches. And so to do that, we have to first convert miles into feet. So you may know already that in 1 mile, there are 5,280 feet. And so notice, again, the miles are on the bottom, so they cancel with the miles up top. So now we're into feet. We can multiply that to get into inches. So we know 1 foot is 12 inches. So these will cancel, the feet here and here. So now we're in business. Now we can relate it to what we have over here with the 22 pi inches. Recall again, we're trying to get to radians. And so we're going to do this thing where we know, again, the distance all the way around the outside of the circle is 22 pi inches. But if you're rotating all the way around the outside of a circle, well, first of all, notice we're trying to get our answer in radians here. So that would mean we're actually going through 2 pi radians. Right? 22 pi inches rotating around the outside of the circle is going to be the same as going through 2 pi radians because you go all the way around the circle. All right, so here the inches will cancel. We can also cancel the pi's here and here. And then we can do some work with our calculators and multiply across the top. Doing that will give us 3,801,600 radians over, multiplying across the bottom will give us 1,320 minutes. And then dividing those two numbers, we end up with 2,880 radians per minute. Okay, so when this wheel is spinning at 30 miles per hour, it's going through 2,880 radians per minute, which sounds like a lot of circles to be spinning through every minute. Okay. All right, using that number now, we're going to do one more calculation. So here we're asked to figure out at what speed, revolutions per minute now, the wheels are rotating. And RPMs, or revolutions per minute, you may be more familiar with. Often they use these with engines, so RPMs. So now we want to somehow convert the answer we just got, the radians per minute, into revolutions per minute. How could we do that? Well, I'm again going to write out the rate we had. So the 2,880, I'm going to write this as radians every 1 minute. And recall a revolution, well, that's a full rotation around a circle, right? So one revolution, if we want to relate that to radians, well, kind of like we saw with one of the steps on the previous one revolution is the same as 2 pi radians. And so when we do that, the radians can cancel, can multiply straight across, so we'll end up with 2,880 revolutions over 2 pi minutes. Go ahead and divide that in our calculator, and when we do, we'll end up with 458.366 revolutions per minute. So that's the number of times that the tire will spin around every minute, which seems really crazy to me. That seems like a lot of spins to only go 30 miles per hour. All right, one more thing on that. For me, in this class, anytime you're given a decimal answer, I want you using at least 3 decimal places. Okay, so notice that I did not round that off to 458.4 or even just 458. We have 458.366 revolutions per minute. So please make sure you're doing that in answers that you submit to me. All right, thank you for watching.